Hi everyone! Today we're diving into a crucial component for power electronics, the gate resistor. We'll explore why it's absolutely necessary when driving MOSFETs and IGBTs, and then we'll walk through how to pick the right value for your application. First, let's understand why a gate resistor is indispensable. When you switch a MOSFET or IGBT, you're essentially charging and discharging a capacitor, specifically its gate capacitance. This capacitance can be quite large, and if there's no resistance in the path, the gate driver would have to supply or sink a very large, instantaneous current. This huge current spike can damage your gate driver, so the gate resistor acts as a current limiter, protecting the driver from excessive stress. Beyond protection, the gate resistor is key for controlling switching speed. A smaller gate resistor allows faster charging and discharging of the gate capacitance, leading to quicker turn-on and turn-off times for the power switch. While faster switching generally means lower switching losses in the MOSFET or IGBT, it also results in higher dV/dt and d/dt rates, which can cause electromagnetic interference, EMI, issues and potentially lead to voltage overshoots or current spikes. Conversely, a larger gate resistor slows down switching, reducing EMI and mitigating voltage/current transients, but it increases switching losses in the power device. Finally, the gate resistor helps prevent unwanted oscillations or ringing on the gate. Without it, the gate and its associated traces can form a resonant circuit with the gate capacitance, leading to destructive ringing that can cause false triggering or even damage the device. Now, let's talk about calculating the gate resistor value. There isn't a single, perfect formula because it's always a compromise between different factors, but we can establish a good starting point. First, you need to consider the maximum peak current your gate driver can supply or sink. You must ensure the gate resistor limits the peak current to a safe level for the driver. A rough minimum gate resistance, R_G_min, can be calculated as the driver supply voltage divided by the driver's maximum peak output current, R_G_min equals V_drive/I_peak_driver. This gives you a baseline. Your chosen resistor should generally be equal to or larger than this value. Second, think about the desired switching speed. This is often the most critical factor. Faster switching reduces conduction losses but increases switching losses and EMI. Slower switching does the opposite. You'll need to check the MOSFET or IGBT datasheet for its gate charge, QG. This parameter is crucial because it tells you how much charge needs to be moved to switch the device. The time it takes to charge the gate is directly influenced by the gate resistor. A common approach is to start with a value like 10 to 47 ohms and then fine-tune it. Observe the gate voltage waveform, the drain source voltage, VDS, or collector emitter voltage, VES, waveform, and the drain or collector current, ID or IC, waveform on an oscilloscope. If you see excessive ringing on the gate or too much dV/dt/d/dt, increase the gate resistor. If your power losses are too high due to slow switching, decrease the resistor, but always stay above your R_G_min to protect the driver. Third, consider the power dissipation in the gate resistor. Every time the gate capacitance is charged and discharged, energy is dissipated in the gate resistor. A good approximation for the power dissipated in the gate resistor is P_dis equals Q_G V_drive F_switching, where Q_G is the total gate charge, V_drive is the gate drive voltage, and F_switching is the switching frequency. Ensure your chosen resistor has a power rating sufficient for this calculated dissipation, often requiring a larger wattage resistor than a typical signal resistor. In practice, many engineers start with a common value, then iterate and optimize based on actual circuit performance, balancing EMI, switching losses, and driver protection. Sometimes, different resistors are used for turn-on and turn-off by adding a diode in parallel with a portion of the gate resistor for asymmetric switching speed control. Thanks for watching. If this explanation helped you understand the importance and calculation of gate resistors, please hit the like button. Don't forget to subscribe to the channel for more electronics tips, tricks, and in-depth guides. See you next time.